you. This is my first PNSQC, and it's really an honor to be here. I've always heard good things about the conference, but it's different when you come and see it for yourself. So just want to thank Philip Liu. I don't know where Phil is right now, but thanks for inviting me. So let's just give Phil, the program chair, a round of applause. Thanks, Phil. And so artificial intelligence, right? And rise of the machines. Are you guys ready for the rise of the machines? Yeah? So today we're going to talk about whether or not we think that artificial intelligence can actually terminate manual testing. And so for those of you who don't really know me, I'm Tariq King, and I lead the quality program at Ultimate Software. I also serve as an adjunct professor at Florida International University, my alma mater. And prior to joining Ultimate, I was an assistant professor at North Dakota State University in Fargo, North Dakota. And I've published quite a bit of papers in this space. As Jason mentioned, I did my PhD and then continued to kind of publish and go along this track. But my motivation for publishing is not what you think. In fact, this is my motivation for publishing. This gentleman, Tariq King Flex Nasheed. And so Tariq King Flex Nasheed is actually a published author as well, but he's actually a New York Times best-selling author. And he's published papers and articles like this: The Art of Macking, The Art of Gold Digging. And so it was one day that I sat down and I Googled myself and I started seeing this stuff, and I was like, I need to wake up. I need to publish more than this guy so that I don't end up getting mistaken for King Flex Nasheed. All right, so manual testing, or simply put, testing. If you ask a room full of people what testing is all about, you'll get a lot of different answers. And the reason there is that testing is a very multifaceted activity. There's a lot of different aspects to software testing. And the definition that I like to draw to for this is to kind of exemplify how multifaceted testing is the definition by James Bach and Michael Bolton. And at the core, testing is about operating a product to check specific facts about it. But there's a lot more than just that. There's a lot of experimentation, exploration, inferencing, learning. And you can't take away from that part of the activity and boil it down to just checking facts. But there's a little challenge that we have today. We have looked at what we call testing, and this topic is really about, can we actually replace that testing activity? But what we call automation today, it's really not very automated. We haven't automated the learning, the exploring, and all those other things. We have to do a lot of work to be able to get to a point where we can automate software, which is still a manual process. And so I know what you're thinking when I start to talk about this stuff and I'm in a room full of folks who are testers. Well, you start to think, well, that is just impossible. We're never going to automate testing, not true testing. And I want you to understand that the word impossible is not just a word. It's really a mindset. And we have to do better as a community. And so I just want you for the next hour or so to kind of dispel that word. Because it always seems impossible until someone does it. And then it's like, oh, of course, that's so easy. Of course, why didn't I think of that? But today, for an hour, just let go of that word. So I'm going to tell you a story, and the story really starts from the end. In other words, it's game over. Artificial intelligence has already terminated manual testing. And the reason that I say that, and the reason that I tell this story backwards, is because if this is really our world, then this is software. And software is literally eating our world. But if that's software, then this is artificial intelligence and machine learning. And artificial intelligence and machine learning is literally going to eat software. And when it's done eating software, guess what? All eyes on us. And so artificial intelligence, it's the science of getting machines to imitate intelligent human behavior. And are you worried at all? Are you a little bit worried? You see, Hollywood certainly tries to make us worry.
Are you saying that robots are going to destroy humanity? And is that a scientific argument or the pitch for an amazing movie?
There's a story that scientists built an intelligent computer. The first question they asked it was, "Is there a God?" The computer replied, "There is now," and a bolt of lightning struck the plug, so it couldn't be turned off.
Holy shit, that's the most terrifying story I've ever heard.
Yes.
In the beginning, there was man, and for a time, it was good. But humanity's so-called civil societies soon fell victim to vanity and corruption. Then man made the machine in his own likeness.
A digital frontier to reshape the human condition.
Replicants are like any other machine. They're either a benefit or a hazard.
Thus did man become the architect of his own demise.
Try to create a suit of armor around the world. Artificial intelligence.
You're all going to die down here.
Human beings are a disease, a cancer of this planet. You are a plague. And we are the cure.
To protect humanity, some humans must be sacrificed. To ensure your future, some freedoms must be surrendered.
What's the problem?
I think you know what the problem is just as well as I do.
It can't be bargained with, it can't be reasoned with, and it absolutely will not stop.
I was designed to save the world. There's only one path to peace. Their extinction.
Greetings, Professor Falcon.
Hello, Joshua.
How about a nice game of chess?
So how about a nice game of chess? You know, seems like a long time ago, but 96 and 97, IBM's chess playing computer Deep Blue defeated world chess champion Garry Kasparov, the reigning world champion. And how did that happen? Well, at the time, if you think about it, it was really about brute force computing power. You see, Deep Blue had dedicated hardware. It could process about 200 million moves per second. And so let's look into that, into a sub-branch of artificial intelligence, game theory, and specifically look at the concept of a game tree. You see, a game tree is really a search function that examines all possible moves of a strategy game like chess. But let's first look at tic-tac-toe. You see, at any given point, we could unfold the game tree for tic-tac-toe and look at every state in the system, and also knowing every single state and every single transition from that state that also leads to an outcome. If we have that tree, at any given moment in time, in any given state that we're in, we can kind of know through brute force checking which is the right move that will move us towards a favorable outcome. But like I said, chess is a bit more complicated. You see, the game tree for chess is a lot larger, right? See, from the start state, you have about 20 possible moves for the first player. And of those 20 possible moves, you have 20 possible more for the second player. And then roughly about that, and you can kind of see how this starts to explode. But nonetheless, Deep Blue was able to search somewhere between 6 and 8 in terms of depth, all the way up to 20, and defeat Kasparov. But let's stop to think about that. Like, how do we think Deep Blue would do against present-day Kasparov? Do we think that Kasparov is better with his age? Or worse? Or maybe that's not a fair comparison. Maybe we'd have to put Deep Blue against the current champion. Well, I really don't know, and actually we don't know the fate of the current champion. We'll find out next month if he'll remain the current champion. But nonetheless, come forward to 2010, and IBM was actually still playing games, all right? They built Watson, which is a question-answer system designed to play Jeopardy. So it used a lot of natural language processing, and back then especially, that was known to be a very hard problem to do this type of processing. And then they put Watson up against two long-standing champions of Jeopardy. First, the one with the highest earnings, and then the one who had the longest winning streak. And IBM Watson won a prize of $1 million. And today, Watson still continues to break boundaries: medicine, finance, financial services. Maybe one day we'll actually see Watson run for president. I mean, he just has to be better than the current president, right? But I'll leave that alone. 2016, we saw another breakthrough. This time, Alphago from Google's DeepMind project defeated one of the world's best professional Go players, Lee Sedol. And so what was it really about Go that was remarkable? Go is an ancient Chinese game, and it's actually, in terms of the rules, a lot simpler than chess. But if we start to analyze the state space, we see something different. You see, when it came to Deep Blue and chess, chess has 16 pieces in the start state and 6 different piece types that behave differently. There are about 35 possible moves per state and 80 possible moves per game. And the goal here is to capture the opponent's king. On the other hand, Go has 0 pieces in the start state. All pieces move uniformly, and there's only one piece type. And then there's about 250 possible moves per state and 150 possible moves per game. And the goal of Go is to really capture as much territory as you can of the board. And so when we start to do our numbers and analyze that, we see a little bit of a difference, right? So in terms of the space, chess has a magnitude of 10 to the 120. However, Go, quite a bit larger. And actually, that's more than the number of atoms in the universe. So if we wanted to do a brute force approach, we actually couldn't. And so what was the key to this breakthrough? And the key was really something called machine learning. And machine learning is really about getting computers to act without explicitly programming them. And so let's go back and take a look at that moment where Alphago defeated Lee Sedol.
I think maybe the game ended.
No, I don't think so, because it looks like Lee is still counting.
No, I think he resigned.
Wow, I think you're right. Wow. Wow, wow, wow.
This was the moment a computer called Alphago beat a master of the ancient Chinese game Go. It's not the first time a grandmaster's been humbled by a machine. But what makes Alphago different is that it's the first demonstration that machines can truly learn and think in a human way. Alphago's victory shocked experts in the artificial intelligence community. Many thought such an event was at least a decade away.
So firstly, a few questions. Why is this important, and what's all the fuss? Alphago shows that machines can really learn. How so? Well, instead of using brute force to calculate all the moves it could make, like previous AIs, Alphago used reinforcement learning and neural networks to mimic the learning process of a human brain. Keep in mind that the ancient Chinese game Go has as many more possible moves than chess as there are atoms in the entire universe. So there's no way of just calculating every possible move on the board. That's practically impossible. For this reason, Go is the holy grail of AI, and learning to do such a task from scratch is a huge feat. Further to this, DeepMind's creators say that the algorithm can learn many more things without alteration or guidance. In other words, the AI is general purpose.
We always used to talk about, well, if we could eventually crack Go and have a program that could beat the world champion, then we must have invented some generic, general purpose algorithm. So maybe we're on the cusp of all of that.
If you ask a great Go player why they played a particular move, sometimes they'll just tell you it felt right. So the one way you can think of it is that Go is a much more intuitive game, whereas chess is a much more logic-based game.
So Go is a much more intuitive game, whereas chess is more logic-based. And, you know, outside of the colorful expression of holy grail of AI, which is some dramatization there, how did AlphaGo do this? Well, the key was a type of machine learning called deep reinforcement learning. And really the strategy was to first teach the Go machine how to mimic the moves of human experts. And then after you did it, you did that with about 30 million moves from the database. And what you did was actually put Go to play games against itself. And at first, it wasn't very good. But it didn't have to be good, because as it plays games against itself, it starts to learn later on, this is the whole idea of reinforcement, by the outcome, whether or not those were smart choices. And so, one of the best ways that I like to think about machine learning is to talk about the difference between the ways that humans learn to act versus machines. See, this is my 5-year-old daughter, Soraya. And if we compare Soraya to a machine, machines are typically programmed to follow instructions. Soraya does not like to follow instructions. But what Soraya does well is that she learns from experience. And so machine learning is really about trying to see if we can get machines to learn from experience. But what does it mean for a machine to have an experience? Well, the answer is really in the data. And so you can give a machine data that represents its past experiences. Maybe a number of examples. It has examples of raindrops. It also has examples of things that are not raindrops. And if it experiences or encounters a new piece of data, it can say, hey, based on what I've seen in my data set, what I've been trained on, I think with some degree of certainty that this is a raindrop. And it can try to classify. And it might not be right, it might be wrong at first. But the key is that as you feed it more and more examples, and as you either reinforce or rewrite the learning, it gets better. And so this is an example of what is the classification problem. But the cool thing is that it didn't need to know about the domain concept of a raindrop. You see, this could have been blanket categories. And you could have looked at the data and extrapolated the features that you wanted, and then got the machine to partition the data based on those features. And that's a process called clustering. And so there's different types of machine learning, like 3 basic types. The first is your supervised learning, in which you have well-labeled data, you have knowledge of the data and the outcome, and you're learning based on known patterns. On the other hand, unsupervised learning is about unlabeled data. You have no knowledge of the data or outcome, and that's good for discovering new relationships in the data, discovering unknown patterns. And then there's this idea of reinforcement, which is kind of like almost like a quasi-state where you don't really have knowledge of the data up front or the outcome, but you gain that experience by trial and error. And so in your supervised learning, you see that you don't have that desired output. Unsupervised learning, you do have that desired output. Unsupervised learning, you don't. And then reinforcement learning, you gain it over time. And so if a program can improve how it performs a certain task based on past experience or past data, then we can say that it has learned. And so that's machine learning. And it's incredible because this whole idea of bio-inspired computing, it's amazing that today, even a very loose model of our neural network system is a very extremely powerful computational model. And so how does this work? Well, first of all, you have a layer of inputs, right? And you have your outputs. And this stuff in the middle, like the brain, like your artificial brain, let's just say that that's a magic box. You have a number of hidden layers. And all that happens is that you take your input, you feed it into the magic box, and out comes your output. And for machine learning systems, you compare and say, well, this was good or this was bad. So you can reward or punish. And so the cool thing about neural networks is that a neural network with just one hidden layer can approximate almost any function. So it's very, very general. And so if you start to think about neural networks and you start to think about having many, many hidden layers, that's where this idea of deep learning comes from. And deep learning, as you saw for AlphaGo, has been applied to several different problems, right? It's a very general purpose approach. And one of the areas that is done well is this idea of self-driving cars. A very hard problem to script out in a very procedural way. But we've done it using machine learning. So let's take a look.
Holy cow. Whoa. Whoops. Wrong way. Ooh.
So yeah, the robots are driving cars. Scary, right? Nonetheless, we see the power of machine learning. But what do all these breakthroughs really have to do with software testing? Because we're here to talk about testing. And that brings us to Act 2, which I like to call Powerup. You see, if this is software testing, then these are the grand challenges of software testing. And when we talk about automation, these are our current techniques. See, those current techniques don't take us very far when it comes to those grand challenges. But maybe artificial intelligence and machine learning can be that power up that we need to really make a difference and help us to overcome those challenges. And to do this, we're going to go back to 1975 to some fundamental testing theory. Goodenough and Gerhardt wrote a paper in 1975 about the fundamental theory of an ideal test. And really, a test is about treating a program as a function of input to output. So you throw the input in, and you get your output. And so that space, or that domain D, is all the possible inputs to the program, and that produces all the possible outputs. And on input D, to the program, out comes f of d. And what do we do as testers? Well, we ask ourselves, is f of d an acceptable result? So in other words, we say, is it OKD or not OKD? But wait a minute. That looks very familiar, right? I mean, it's almost like if we wave the magic wand, all of a sudden, we have a machine learning system. But hold on, let me not get too far ahead of myself. Let's go back to the testing theory. And so really a test set T is you take a subset of that domain and you feed it to the program, and you have to verify that for all of those tests, they're successful, they're OKT. And what do we do as testers? And this is where the theory comes in, the ideal, is that if that's an ideal test, that somehow implies that for all of those tests that we did, it somehow must mean, if that test passes, that all the possible outputs produced by the program are okay. In other words, for all T and T implies that for all D and D, OKD. I mean, that sounds like a crazy thing, but it gets crazier, right? Because this is what we do as testers every day. We try to bridge that coverage gap. And it's no wonder that we run into problems, right? The first thing that happens is that the first bomb goes off and we realize that we're in the middle of the year. And right behind us is this problem called input space explosion. And where there's input space explosion, you know that there's output space explosion. And where we have inputs and outputs, guess what? There's state explosion. And yet we're still trying to manage this with this truck behind us. Like, that's you. Y'all realize that that's you? Like, if that was me, I would want some help, right? And so my friend Jason Arbin put it nicely in a blog post. You know, we look at software and we add features to software, and that complexity grows exponentially. But how do we add tests? We add tests very linearly. And so there's no wonder there's a coverage gap. And the whole idea of AI-driven testing is to see if we can somehow leverage AI to break through that coverage gap. And so I gave a keynote last year at SoftTech Asia in Malaysia. That's where I met Phil. Talking about these AI-driven testing services. You see, I was starting to see, as we were researching this problem at Ultimate Software, I was starting to see a lot of different services come online leveraging or claiming to leverage AI for testing. And I really wanted to get to the bottom of it. So I talked to a number of vendors and I shared my experience in that story about that. But as we continue to go, I'm seeing more and more vendors doing this stuff. And trying to figure out like who really has bots, and if there's really bots, like are we really doing this? Was a little bit of a challenge at first. But I'm here to tell you today that the bots are already here. Yes, AI is already testing software. And these are two different solutions. One developed internally by Ultimate Software, and the other one commercially by Test.ai. And these bots are exploring software like humans. And they're using testing techniques. And they're doing exploration and trying things and failing and then getting through them. You see, the bots are actually mimicking the idea of human present testing. They're discovering, modeling, interacting, observing, and learning. And I'm going to walk you through how this works. But I'm going to do one better later. So the first part of it is that the bots need to perceive their environment. And that includes the application, the interface, the structure, the behavior, the flows, any differences that it saw. And it does this and builds models, just like how we build our model after we see things, right? And we can kind of keep track of that environment using that model, or we can somehow manage uncertainty, right? If we can't see something at a particular moment in time, or remember that we saw it, now we don't see it, just like humans. And it can interact. So you're talking here about somehow finding a way to interact with the system under test, maybe observe its behavior and make some sort of evaluation based on that observation. And just like us, they learn, right? They get feedback on the quality of their actions. And so to give you an idea, if this is your app, it starts to piece it apart. And it does this in a very general way. You can train it on images, you can use aspects of the DOM, and then it builds models of that, both of the application under test, and it can actually build a model of your testing effort. And then to interact, it uses machine learning, right? So it's not hard-coded stuff. It will try something, right? It might tap on the menu bar, or it might try to pinch to zoom. And then it gets learning, kind of gets feedback so that it can improve, either reinforce or rewritten. And it can do that and apply that to many different applications. So same thing for observing outputs. It uses that general mechanism to do so. And so at Ultimate Software, we started the Dora project. And Dora builds models, discovers, it crawls the application. It's actually a screenshot of Dora discovering our application. I'm building this model. And we can interact with this model, but the model is really more for the machine. And so we look at that and we analyze that web interface. It can interpret constraints, labels, and know, well, this is a phone number, or these are error messages, and these error messages tell me something about what was coded in terms of maybe the boundary values for this field. Doesn't make it correct, but it's there. We can leverage it. And that state transition and that data model of the flow through the application, it can retain that information. Dora also generates tests. There's an example of a boundary test for a human-readable format generated by Dora, right? You navigate to a page, you set some widget, and you go through. And so this test generation uses different methodologies, as I mentioned, boundary equivalence classing. There's test execution, which wasn't very hard to automate. We've been doing that for a long time. And then the logging as well. But my favorite part of this whole thing is the learning. And so we've done some work to train Dora to pick apart user stories and the sentences there using natural language processing. But that's a very challenging problem to then use that information. So we do it pretty well, but using it becomes hard. Then we realize, you know what? A better artifact for us might be to train it on test cases or abstract tests, because the abstract tests have what your setup conditions are and what your expectations are, because that's one of the hard problems, is to really solve that Oracle problem, right? There's a lot of open problems. But I don't want you to believe my word. I want you to go see it for yourself. So we wrote a paper, and that is going to be presented by Diony Santiago. Diony's in here somewhere. Oh, right there. And as part of his job and as well as part of his master's thesis, he wrote a lot and did a lot of the work to make us be able to learn from abstract tests, define a language, build some tools that trained some neural networks to do this stuff. So I encourage you at 110 to go and look it and watch it live, watch it happen. Like watch machines and humans test together at PNSQC. And if you want the details, it's in the paper. And I encourage you to kind of use that as fire to say, hey, you don't have to be Jason Arbon from test.ai to do this stuff. You just have to have the motivation. And Jason thinks he's slick, right? He has a session here on AI too, but he didn't put AI in the title, but I found it. Because what he's trying to do is test the world's apps. So look for that session too. Because what we're doing in the context of Ultimate Software and trying to push our testing forward is cool, but he's doing it at a whole other scale. So look for that as well, and go and see these things and understand them. Because as testers, we need you to understand them, and we'll talk about that. But in general, these things are leveraging machine learning models. They're using things like test drivers like Appium and Selenium and different frameworks like that. And they're combining that with cloud computing. And the result is a very powerful thing. The only way that you test the world's apps is if you have accelerated coverage. Because we see what testers are dealing with. And there's a lot of benefits to AI-driven testing. The first is very general purpose, right? Can apply to almost different types of testing, any app, any domain, you think of it. And we've all heard of the pesticide paradox, right? Where we are testing the same things over and over. Well, AI generates new tests every single time. Of course, you can rerun the same test if you want, but that's the power of it. You can use it however you want for whatever situation you need it for. And it's on a large scale. So you're talking about deep learning, you're talking about cloud computing. But the current state of the art has some limitations. And I'll give you a hint. One of the biggest limitations right now is that a lot of the vendors, they're looking at this problem from the outside in a black box fashion. But a lot of testing today happens from the inside. So we have to start tackling that. But that's not even my biggest fear. My biggest fear is something like this. Is that when we put these systems out there, they're not done. They're not done being tested. And we talked a little bit about that during the panel. But if you go back, like our traditional programming model was about inputs, and we write a program function, and we produce outputs. But with machine learning, we actually start with inputs and outputs, the data. And then it constructs that function for us. And guess what? Every time we train the system, every time we add an input and kind of tell it yes or no to an expected output, we're in essence rewiring that function. And what would we do in the software industry if we changed our program? Well, we rerun a whole bunch of tests. We don't just walk away and be like, hey, that's cool, you changed the program, that's production. And so another huge gap, which is very dear to my heart, is about designing these systems with testing in mind. You see, my PhD dissertation back in 2009 focused on just that. You see, IBM and Microsoft and HP were talking about building the next generations of systems. And they weren't talking necessarily about artificial intelligence, but we were talking about systems that can dynamically adapt and heal themselves, configure themselves, optimize themselves. But you know what no one was talking about? The fact that if you're going to do all this dynamic behavior, system needs to be able to test itself. Like self-testing needs to be an implicit characteristic of these types of systems. Because what happens to quality? And so that was my work. How can we design the systems and put the bots on the inside? Because you see, if the bots are on the inside, it becomes very, very powerful. You have access to production monitoring, what real users are doing, real scenarios, real issues, real data, real environment. You got everything that equates to real learning and real intelligence. And quite frankly, some bugs can't be found in the lab anymore, can't be found in the lab. And so my work proposed some approaches. And you start to talk about systems that can test themselves or in production, you start to worry. Oh, everyone gets nervous, right? Because safety is an issue, right? If you have live users, you need to bring that system into a safe state so that if you're going to do testing in place on the actual system, you make sure that all the external users and their processes are blocked, and that's a hard problem. Another alternative is to make a replica of some aspects of the system and do your testing there. And I think that a lot of this work was almost before its time because we didn't have deep learning and all these things. But nonetheless, now that I look at the space, like this is the time. And so some of the benefits that we mentioned to this whole self-testing thing or designing systems in this manner is about those users, the scenarios, the data. You're now on the inside, so you can have more targeted testing, faster feedback. And it's very complementary to the black box stuff that everyone else is doing, right? Imagine if you can start a test from the outside, but you also know how to test from the inside, then you can see, well, here's where I think the issue is. You can do better debugging and isolation. And it kind of promotes something that I think is very interesting. If you can start to do that, and you can start to monitor the fixes that go in. Maybe you can start to build a system that doesn't only detect that there's an issue, but it recommends the fix and maybe applies the fix, and the system is self-healing. And all this sounds like, wow, out there. But let me tell you something. Right now, AI is, you just saw it, able to drive cars. And there's a lot of problems out there that the advances that they have in that space are directly applicable to software testing. We saw how the testing problem and machine learning kind of map to each other. We're actually doing the same thing, right? But what about driving a car, right? You're on a journey, and there's some starting point and some destination, some goal. And along the way, you take paths. And there's obstacles or limits. There's threats. We have threats, we have boundaries, we have limits. And so I challenge you to start taking a look at some of the research that's out there, because all of these things map to things that we care about in the software testing world. And maybe we can use that image recognition research and that autonomous control, real-time decision-making, path generation, anomaly detection, runtime modeling, all for the purpose of testing software. Because it's not impossible, because things that we thought were impossible, I remember the days where voice recognition was impossible. Hard problem, we'll never solve it. Well, I asked Alexa the other day if voice recognition was impossible, and she said nope. So that brings me to Act 1, the beginning. And the beginning is all about us as testers, recognizing that artificial intelligence and machine learning are here. They're right in front of us. And in fact, they're not caged up. They're outside. And we already have AI and machine learning embedded in software. And people are using it, and not for driving cars. They're using it for the software that you do in your day-to-day lives. And if anything is going to stop artificial intelligence from taking over, it's us. Like, we are the community of testers and quality engineers and quality-minded folks that know that to really test something, you have to understand it. And to understand it, you have to do things like observe it, model it, control it, evaluate it, and identify any risks surrounding it. And so my challenge to you is really about recognizing that we have our part to play when it comes to artificial intelligence and machine learning. You see, these systems fail. And when they fail, they can cause a lot of issues. And then there's problems like overfitting, where you get random noise and you have security threats. There's time and cost, and all that's money. And we're putting more and more on this technology. And so, it seemed like yesterday, but it was 2 years ago, that at the Star West conference I gave a lightning talk. And my talk was really about testing being lost. And that we need to really bring back testing. And the way that we do it is through innovation. Because we have lost a sense of innovation, in my opinion. We have settled for a substandard definition of automation. Like back in the 1950s, when we talked about automation in the manufacturing industry, there was this concept of lights out automation. It means that we could automate so well that we could turn the lights of the factory off, because the humans weren't needed to continually man the machines. But we don't have lights out testing or test automation. In fact, we have a vision so far that's focused on manual testing. Yes, all testing is really manual, because even the scripting that you do for automated testing is manual. And the only thing automated about it is the execution and the logging. Yay. And so we need to refocus as a community on a grand vision of testing, where testing can be done with no human intervention. And so it was a little over a year ago that Jason and I started an organization called the Artificial Intelligence for Software Testing Association. And this whole idea of AIST is this emerging field that centers around developing AI systems to test software, methods to test AI systems, and ultimately designing systems that are self-testing and self-healing. It's the intersection of these three worlds, right? The tools that we need to drive AI testing, testing AI systems and those methods, and designing self-testing systems. Because you see, we really need to come together as a community and get serious about this problem. Otherwise, we're going to be left behind. And this problem is so big, so important, so large, that not one company is going to solve it. It's only going to be solved by collective intelligence. Just like how the machines are better because of collective intelligence, we are better because of collective intelligence. And we can't lose that. And so AItesting.org is a place that you can go to keep up to date on what is happening in this space. And the reason behind it is really about just promoting that study of AI and machine learning as it pertains to testing and quality, facilitating cooperation, collaboration, communication as we pursue this grand vision of AI for testing, holding conferences. We held a conference, a virtual conference earlier this year. We've had several different types of events at different conferences, and happy to be here and give a panel here that was unexpected. But like, we're talking about this stuff because we really need to share those views, those ideas. That's how we get through this. And it's really about disseminating that knowledge and that experience so that we don't, one of the reasons that I found Jason was I was looking for someone who was working on this stuff. And as I went to one of his tutorials on mobile testing, he showed these bots. And I'm like, that's what we're doing. Like, he's doing what we're doing. And I just couldn't wait to go talk to him. And the cool thing, to his credit, is that he openly shares and geeks out, probably overly shares. He also rants a little bit, but that's okay. But through that collaboration and that communication, you're able to not make the same mistakes and learn from the experience of others. Isn't that what we just talked about? How machines learn? Well, that's how we learn, right? And so here we are at the end. Well, since I told the story backwards, we're not really at the end of this. We're actually just at the beginning. And the reason that we're at the beginning is because this is the beginning of innovation in testing. I've never seen the software testing industry buzzing so much about something, and I'm just happy whether or not people are doing it for real or they're faking it, at least people are interested and people are doing things, and we're not just settling, right? So I just want to thank you for this time, and I encourage you, look into this stuff. Do what you can. Educate yourself. We mentioned the other day, you don't have to have all these degrees. Like, Jason makes fun because he doesn't have a PhD and he really wants one. But you can do this stuff, right? Just dig in. So thank you for your time. All right, so I guess Michael set the stage for questions, so let's do it. Any questions? I see one back here, one up here. I don't know how you're going to do that. This is the first hand up.
Let's start with this direction, then we'll toss this way.
Cool. All right, we've seen you. Don't worry.
I need some AI testing here. So my question is about, this is good. My question is about a new application. Suppose I'm developing a new piece of software and it's innovative and creative and I want to test it with an AI system. How does the AI system learn what expected behavior is?
So that's where, well, first of all, we all know that that's a hard problem. If we had solved that problem, we wouldn't all be sitting here just trying to converse, right? But there's several different ways that it can kind of learn expected behavior. One of the approaches that I mentioned was Diony's work, and it's actually pretty cool. An actual test script has a lot of information, including certain expectations. And you can have a test case that's very low level and very concrete on what happens if I put this input in this field. Or you can have an abstract test that tells you what the expectations are of a particular workflow or business process, right? And so Diony's work actually looks at how can I actually feed the machine with this natural language and get it to start generating new tests. And so that's one of the approaches. There's other things that you can do, like we mentioned in the talk. You can train on images and get it to know when it has detected that something is wrong. And some of those things might be very obvious and easy. Others might be more subtle because there's a lot of domain knowledge, right? So it's really all about training. And it's not an easy problem. It's not a solved problem, but it's a problem that I think we need to collaborate on and get better at, right? Because, we build HR and payroll software. There's a lot of complexity there, and it's not trivial. And then that's always moving. And so I think that we have to be building systems where we can teach software or teach the bots what is the expected behavior and keep teaching it. It doesn't stop because our government policies for compliance and taxes don't stop, right? And we have to keep updating our software to do that. So in a similar fashion, we got to do it to teach AI. All right, where are we? Okay, yes, sir.
So in the short term, what are the areas you think that AI does not do testing well? And then more the medium term, 2 to 5 years, say, I'm just curious what areas AI will be used in first, and what areas do you think, at least in the medium term, humans will always be involved in terms of testing?
Yeah, so that's a good question. I think that, I think that as a tester, we're always risk-based, right? I think there's a couple barriers to where AI will, and I'm going to separate what might be some of the artificial barriers because we as humans are not comfortable with that, and then separate that from maybe what are some technical challenges that I see. We just had a very good example of something that's not an easy problem to solve, right? Even with all the advances that we have in the AI for testing space, that Oracle problem is a very hard problem. And especially where there's interconnected domain knowledge, there's a lot of these things that need to be captured. Until we actually capture that stuff, it's not that AI can't technically do it, because I believe that with the right training and with the right data, it can get there. But we have to continue first to build tools to do those things better. And we're starting to see an age where we're building neural networks that can auto-tune other neural networks, and we can kind of reuse. The cool thing is that if we build up that knowledge corpus and we train a system, we can reuse it. So I think it's going to take some time, not because there's necessarily technical challenges there, but I think that humans, where you're going to see humans a lot are anything that's mission critical or safety critical. And I don't think we're going to be open to trusting the machines. And I think there's even a lot going on right now when you start to think about the implications of a self-driving car and things that can go wrong there. That stuff is to me more of a people thing than a technical challenge. But there's still open problems. Everything that you saw there in the talk, input space explosion, the Oracle problem, state space, reducing that. I mean, all those things are tough problems that are still relatively wide open. We're getting better, but we're not there yet. Sure.
Okay. Just one quick follow-up. Do you think AI would be good for, one of the tests we do is just how easy is this to use for a human being? Is that something that AI would be good at?
Yeah. So, So the question was really about sometimes we look at usability and how easy something is to use, and we have to test that, and that's something humans typically have to be involved with that we've deemed not easy to automate. And the truth is that there's some vendors that are doing that already, because a lot of the work that's being done on image recognition and looking at things from that standpoint, once you teach the machine the patterns to look for, it can start to do that usability testing. And so there's this whole field of visual UI testing, and Applitools is a vendor that's actually doing some of this stuff using images, and I think that stuff is definitely going to be able to be automated at some point. They're already making strides on that. So I don't think that that's going to be a barrier to artificial intelligence and testing. Where are we now? Yes.
So I also have a mathematical background, so I find the whole thing fascinating.
Cool.
But
I've also worked for incredibly large projects before in industry, and you have a product owner, you have many product owners, and you might have the same, the punchline is that you're logged in, but you might have different workflows to get there depending on what part of the product you're in. And generally they're like, these are the steps, here's the screenshots we expect. And so I fail to see how artificial intelligence can even play a role in this anymore, because I'm assuming that okay, I finished this functionality, I've recorded maybe through Espresso or something like this that exhibits this functionality. Here's a test that exhibits this functionality. And I could see as you train an artificial intelligence, some product owners would be like, no, that's not what I wanted at all, even though you learned how to get to the punchline. Because product owners aren't so much concerned, they're concerned about the punchline, but they're also concerned about how you got to the punchline. Because that's how they get promoted. That's how they show that they've understood the product.
Yeah.
So could you give me some insight into how this will even help in this type of situation?
Yeah. So one of the very cool things about artificial intelligence and the approaches that we talked about, especially things like reinforcement learning, is that you're right. There's multiple different ways to flow through the system and to get to some result or some goal. The cool thing is that AI is very good at doing that, right? In terms of discovering those paths, right? And for example, you can build a system such that you could query and say give me all the different paths that you've traversed from point A to point B. And maybe you're right. Maybe at some point in that, there's a lot of these different ways to get to that goal, but it didn't take the path that you wanted it to. To me, that's just a training exercise where the product owner can start to specify, and maybe for that particular type of application, this is a common path, and that's a data point for training. And over time, as you continue to do that, it will get better at finding those particular paths or those particular scenarios. The other point is that when something changes, as you evolve the application, the cool thing about AI is that it'll go into that trial and error mode where it can now discover a different way. So if you remove something and that transition no longer exists, maybe there's another way to do it, it can kind of try to start to discover what are some ways that I can get to that outcome. Similar to how you play the game of chess, right? Or you play the game of Go, and you see the outcome, and then you get better as a result. It can go into that mode and do that.
But what I mean is the process, the path to get to the goal is just as important as the goal, right? As a product owner, there's a punchline, but they don't want any way to get to the punchline. They want their way to get to the punchline, which means they already have to test.
Sure. So let them feed that in up front. Feed that in up front as something that they want to see, and and the system can actually use that as part of that. So all I'm saying to you is that anything that is outside of the knowledge or the learning, is something that can be provided. And remember, I talked to you about training these types of systems. Those are things and scenarios and cases where you want to provide that information up front, because if that's really business critical for them, then you want to make sure that those things are covered. And the cool thing about it is that if you really want to get granular with exactly how to get someplace or how to get to that punchline, then you can. And if you don't, if you just want to specify the intent, my goal is to do X, then the AI can figure out that as well. So we can talk afterwards, but that's definitely something that I think is doable, right? All right.
We got enough time. Is there any more questions?
Oh, right here?
John.
Oh, man. I'm nervous now.
You knew I was coming.
Yes, I know.
So it occurs to me, kind of building on what the last gentleman was talking about, is that we're moving into call it a phase of computers and software. I've heard that programmers may have a limited life expectancy also. And so it moves things, I'll call it, to the front side, where items like the architecture and the grand vision for what the software is going to do, or in our case, what the software testing is going to do, will start becoming, I'll say more relevant, and that we will then have to work with the AI systems to I'll say, realize that grand vision or the architecture or the model. So it seems like there'll have to be some kind of collaboration until they really reach sentience, which that's a debatable issue, of course. But would you agree that the job for a lot of us is going to move into the, call it more upfront side, working with the AI to do the nitty-gritty of things?
So, I mean, I agree with your position of the question, right? Like, if you start to think about this, right now we're here talking about testing, but even engineering as a whole, a lot of these things, architecture, like I think no one is really like quote unquote safe from this technology because it's so generally applicable. I do think that we will end up, just as with any technology, being able to shift our focus onto other things and collaborating with the technology to achieve our goals, right? It's no different than we do today, right? It's no different. Like I sit around and I think, you know, from when I was a kid and when I go to the airport now, where I go, like technology has really, like software has infused our lives and transformed our lives so much that we're collaborating with these machines every day, right? Now they're not very smart machines, some of them right now, but I think artificial intelligence and machine learning it will be just as transformative as software was to our lives, right? Because it has that potential. And so I do think you're going to see a shift in how we use software, what we can do with software, how we validate software, and whether or not, I'll leave that topic for Jason. He likes that whole sentient. But it's happening. It's happening already. All right, I don't know how much more time we have. Okay, here we go.
When you say self-healing systems, what exactly does that entail? And how would a system that, say, tipped over in production spin itself back up?
Yeah, so, I mean, I remember the days, how many people remember the days where PowerPoint would crash and it would hose your presentation, like corrupted file? I thank God that Microsoft got that right nowadays. I haven't had a corrupted PowerPoint file in a long time. And actually, I remember having the whole thing freeze up and seeing it shut down and start back up, and I actually have lost no data. Like, to me, that was a miracle. I'm like, when did you all get smart? Like, so when I think about self-healing systems, and of course that's a very trivial day-to-day example, but it shows us that there's potential there for systems to be kind of aware of themselves and be creating several checkpoints, and that if something happens, then it knows how to kind of repair itself. And obviously, like a very trivial repair is a reboot. But there's a lot of other things that you can do with the information and knowledge that you have to do something, right? And we're seeing, like, for example, the trend towards microservices and a lot of architectures that can actually help us with things like being anti-fragile, right? So there's anti-fragile microservices patterns where, hey, a service goes online, well, you know what, the system is still up, right? It's no longer deployed on one node and everything is hosed. It's still up, and maybe that functionality is blocked, and it can figure out using its analytics, like, hey, let me ping this service and see, hey, are you still awake? Can we revive you? Or do we need to do something to restore your state? Now there's event sourcing. There's all these things that can bring a system back to exactly the way it was before. And that's what I think of when I think of self-healing, is different strategies for doing that. All right. One more.
Let's see. Let's wrap this up here real quick. Let me see. We got 1, 2, 3. All right. Let's start there and then work our way backwards, and we'll take 3 more. Can you pass it here? There we go. Ready?
Oh. Good catch, bro. Good catch.
It's almost like I was programmed to do that. So you've said several times in your talk, in a bit of a joking fashion, are you scared yet? When you're talking about AI taking over, and keeping in mind that I'm more afraid of non-AI behavior lately. What is it that you're scared of?
Well, I didn't really say that I was scared. I don't know. We'd have to watch back the video. I'm not a lawyer. But if I had to be honest to answer that question, in general, and you're right, non-AI behavior is just as scary. And you know what really scares me is the amount of trust that we put on things without validating them properly, right? That is the ultimate thing. And I guess as I see us put more and more responsibility or more and more autonomy on the software itself, and that's where I think artificial intelligence pretty much takes that to another level for me. That's where my fear comes in, that we continue to just blindly trust systems, not do our due diligence to get in front of because testing always lags behind, right? Like we always leave testing for last, right? So that's really the only thing that I'm scared of. You should talk to Jason though, for sure, about fear of this stuff because he has a whole new level. And I'm trying to see if I believe what he says, but I don't know, but we'll see. But yeah, that's my real fear is about trust and not doing our due diligence.
Thank you.
Yep. All right.
So you describe the F of D and how we have these inputs and we have these outputs, and testing is kind of creating the inputs and the outputs. But sometimes the F of D, or the test is the F of D the right F of D? Did I actually choose, did we pick the right algorithm? And in that same vein, we have these kind of political aspects that are not necessarily part of the direct aspect of testing, but there's some politics, we're actually going to pick the not best algorithm because human beings want that one because it's less scary. I think of Target and their mailing to 15-year-old kids saying, here's some baby products, which created a whole big mess. And obviously they were right. The AI was right, but it was wrong for humans.
Yeah.
How do we deal with that?
Yeah, well, the way that I deal with that is that as humans, we have to be the ones watching these things and knowing what we want and making a call as to whether or not that F of D is the right F of D and if its behavior is good. And if it's really something that we may not want to leave to the machine, then why use an AI approach anyway for it? Why not just specify it in the traditional way, especially if it is something that can be solved in that way? I think that as we use machine learning approaches, that we start to think, hey, this machine learning is giving me something that I can't get using the original approach or the traditional approach, I should say. And if that's the case, then use it. But if not, then why? There's actually parts of our research project that we don't use artificial intelligence for because it's pretty simple. Calculating boundaries on a field, that's pretty straightforward to do in a traditional algorithmic manner. So why use machine learning for it? If we find a better case for it, then we will. But using machine learning where it makes sense. All right, I think we have one more question.
We have the last question. All right. Winner, chicken.
So as a novice who's about to enter AI 101 class as a student, where would you suggest I look, say, 3 topics to begin as a tester to appreciate this and have some understanding going forward? Because I know virtually zero about this.
Yeah, so you're saying 3 topics of as a starting point that you can go for, right? My first instinct is always to, and I think we try to do that in the talk, is to get a baseline fundamental understanding of artificial intelligence. What are some of the different approaches? There's a lot of different machine learning approaches. I mentioned some of them in there, decision tree learning, different models. But just getting a basic understanding of that, there's a number of online materials that you can look at. Stuart Russell has a book that's like the Bible of AI. I recommend that people get that book. But that has a lot of information, right? Andrew Ng, NG, has a lot of videos. There's a Stanford course out there. There's a self-driving course. So there's a lot of ways to get that fundamental information. So I would start there to just understand conceptually what machine learning is all about and some of the different approaches. The other point of topic that I would start to go to is really is trying to less conceptual and trying to understand like how do these things actually work in practice, right? And I'm a firm believer of trying to get your hands on hands to keyboard in some forms, right? And Jason and I actually just we teach a course that we designed to introduce testers to these different AI and machine learning skills. And one of the things that we like to do is to just, whether it be a tool like Google has their AutoML Vision, there's some Python libraries that you can put together. There's, we created some Jupyter notebooks to kind of give people a feel for how do we either program these things to start, or how can you use something off the shelf that someone has already trained and get a feel for it. So my second point to you is really about getting your hands on something. And then the third area, so you have your fundamentals about how this stuff works. You get your hands on how to use it kind of in practice, even if it's either getting deep into programming in Python and that sort of stuff, or using something that's available like AutoML Vision. And the third point that I think is important is understanding how you can test these systems, right? That's the other area of it, is how do we actually measure either the accuracy or the precision or the recall, or go about seeing if the models that you've built are actually good models. And there's a lot of room there, I think, for us to contribute, but just getting a fundamental understanding of how classification problems are evaluated. And again, a lot of that stuff is online and in books and so on and so forth. Jason actually wrote a great blog post with a whole bunch of stuff on pointers and where to start. So maybe we can share that as well. But I would try to get into that. So.
Your own organization as well, that is a good sounding board for
Yes.
baselining that too. So,
yeah.
Guys, Tariq, give him a round of applause. What a great intro.